Everyone, and welcome to another session of Goblin Test 1.3 Integration and Interlinking Knowledge Graph. And today we will welcome our speaker, Daniel Garijo. So Daniel Garijo is an associate professor in the Ontology Engineering Group at the University Politécnica de Madrid, UPM. Previously, he worked as a researcher at the Information Science Institute of University Southern California in Los Angeles, where he also completed a postdoctoral fellowship between 2016 and 2018. Daniel's research focuses on knowledge engineering, open science, and semantic e-science, particularly on capturing the context and metadata of scientific software and computational experiments to promote their reproducibility and reuse. To this end, he has proposed methods for creating knowledge graphs with data from computational experiments exposed as objects accessible on the web. At international scene, Daniel has participated in W3C standardization groups, W3C provenance working group, and is currently involved in the Code Meta community to define software metadata standards. The consortium of scientific repositories and registries, which brings together more than 24 platforms for describing scientific software. In addition, he actively participates in European open science cloud groups for FAIR and Metrics, and is a member of the Research Data Alliance Group on FAIR and Machine Learning, which he co-leads. Daniel has participated in more than 20 national and international research projects, successfully carried out for agencies such as DARPA and NSF in the US and European Commission in Europe. The standards he has helped develop has impacted hundreds of researchers in industry and academia. So welcome, Daniel. You have the floor. Thank you very much.
Thank you. Thank you for the thorough introduction. Today, I'm going to be talking a little bit more on the knowledge engineering side because of the topic of the talk today. And even though I participated in thoroughly in this effort, I also want to acknowledge my colleagues, Maria Poveda, Jia Ji Lee, and Si Yuan Clark Wang, and other ontology engineering group members who have, without which this work would not be possible. And by the way, if you miss anything about this talk, or if you want to hear more, my colleague Maria Poveda will present it at a workshop at ESWC in a couple of weeks. So in case we don't have enough time for the discussion, you know where to continue the debate. So the topic for today is towards explainable agentic ontology engineering. A lot of buzzwords put in one title. So let's see if the talk meets the expectations. I wanted to start a little bit with a small background on ontology engineering, right? Which has a long history. Long, I mean, well, more than 30 years of history now. Our group has participated in contributing with ontology engineering methodologies, right? You have things like methontology from Asunción Gómez Pérez, Oscar Corcho, and others participated. Then you have things like the NEON ontology development methodology. So in the end, what all these ontology development methodologies propose are different tasks to structure the context, well, the activity of contributing into producing, developing an ontology, right? So from Groninger and Fox, we have the competency questions technique, which I'll bring, which basically capture the requirements for the ontology, and I'll bring some interesting insights about how people use them in a second. Then we have a more agile techniques like the diligent framework or rapid out frameworks and XD methodology. And now we have seen in the last years, at least a methodology that has been proposed by members of my group has been the linked open pairs methodology. And in general, even though I'm simplifying quite a bit in this slide, has four main steps, activities, right? The ontology requirement specification, the ontology implementation, ontology publication, and then mandate. which they kind of mirror the types of things that you would do in a software engineering project, right? You gather the requirements, then you implement, you do releases, and then maintain. For each of these activities, there are different artifacts that are involved, no? In the requirement specification, you have the CSV usually, or this Excel spreadsheet where you keep the requirements. Then the ontology implementation will yield an old file, which then you put in on the web following the linked data principles, and then you see that you have documentation and the old file or the different serializations of RDF. And finally, with maintenance, basically you come up with new requirements and you review the whole process. So that's a little bit the context on ontology engineering, right? And the thing is that throughout the years, many different tools that have been developed by the community, semantic web community, to help in these different tasks, no? So for example, we have tools like RDFlib and Protege and Choke, which will help you validate the syntax of your RDF files, to create actions in a graphical interface, or that even create diagrams that to later get the old serialization of what you're looking for. You'll see things like the linked open vocabularies where you can go and reuse existing ontologies and browse existing terms that exist. You'll see tools like OOPS that can be used for evaluating ontologies, themis, which can be used to validate tests of ontologies. And then tools like Ontology or Widoko, which will help you publish an HTML out of your ontology based on the definitions that you have provided, and tools that will help you comply with the FAIR principles, such as FOOPS, right? So the bottom line here is that there are many tools and many methodologies. The challenges, of course, is that each methodology requires some expertise in tool handling, domain knowledge, and usually getting into an agreement, which in the end is the contract, the ontology itself. All these activities require quite a bit of time. And one of the challenges is that in the final product, the provenance of the ontology and the tracking of all decisions is usually not present. That is usually supported in the documentation paper or other artifacts that are usually not in the ontology itself. So the questions that we want to address today is how to leverage large language models to support ontology engineers for these tasks, right? And the thing is that we have been conducting a recent literature survey, which has been published in the Semantic Web Journal by one of our PhD students. And there has been a lot of work in the last couple of years on using LLMs for different tasks. I'm just going to focus on the first two stages. Well, in particular, in the second one, which is the conceptualization task and the implementation, the encoding task. So we see that a variety of researchers have created things, ontologies out of natural language text, out of terms for using LLMs for classification and typing, through ontologies, out of enriching existing ontologies and creating explanations, and even from competency questions deriving a full-fledged ontology, right? But sometimes with some caveats. We also see that other researchers in the encoding part will leverage domain documents with stories, competency questions, or additionally natural language text to derive the old files, natural language text, or actions representing the concepts, classes, and relationships that ontology should have. The actions is less common because LLMs still struggle a little bit in that part, as I'll show later. The thing is that consistently we found some issues with this existing state of the art. No, in some cases it's the reproducibility, because people tend to use closed source models that yield different results because these closed source models, well, they change from the time that the people publish the paper from the time that possibly people want to use it. Alternatively, sometimes the prompts or data sets are not available, right? This is not the case in all cases, of course. We have found this only in some cases. One of the things that we have seen is that consistently there is a lack of tool usage. So all these tools that now the semantic web put to use to ontology engineers, LLMs don't use them by default, right? So that is something that consistently we saw, except for one case, which is the methodology that we build on or work on. We haven't seen many other approaches that behave that way. Also, we have seen that in some cases, the proposed approaches are not aligned with methodologies, with exceptions, with approaches like Neon GPT, which have a human in the loop for conducting each of the activities. And finally, one of the problems that, in my opinion, is one of the bigger flaws is that when the LLMs create an ontology, or each of the approaches create an ontology, there is no provenance capture of explaining the rationale of why a term was added into ontology. And therefore, you kind of, as an ontology engineer, need to go back to the competency questions, find why a thing was there or was not there, and maybe rethink on how to provide feedback for the next iteration. So here's where we get at the contribution of this talk. No, we are introducing MASE, which is a multi-agent system for explainable ontology generation, which is not perfect by any means, as we'll see now, but incorporates a first full iteration for generating ontologies where the input is the competency questions and the output is a valid ontology. This is inspired by the Neon GPT methodology, which basically proposes very similar steps, but with a human in the loop in each steps, and we transform this approach into an agentic approach. So now agents use some of the tools that are commonly used by ontology engineering, by ontology experts, in this case RDF-lib, the OOPS validation tool, and the Hermit reasoner, and we track also the provenance, adding, this is also a contribution of a framework, which each agent states in the ontology itself how each agent added modifications to that term. So that way, when we finish a first iteration of the ontology, the engineers can go and check why was a term added in the ontology. We also use open source models, which of course is far from being completely reproducible, because some of the size that the models that we are using is very high. But at least these are openly available, and with the correct infrastructure, they can be deployed in your local, they can be deployed locally, right? So how does this work? First, what we have done is created a structure so agents can communicate more effectively. The thing is that agents or LLMs, they know all, but they are not very good at creating all by default. So what we have created is the representation in a JSON format initially that we transform into all, that captures all the elements that appear in this slide. Basically, the RDF type, label, comment, for basically stating what is the type and definition of the term, the rationale stating why a term was added in the ontology, the source indicating what is the document that motivated a given term in the ontology, and then some axiomatization, including subclass of, domain and range, disjointness, which we need for assessing logical consistency, and other actions which right now we do not capture very well because they are a little bit complicated, and we are just starting to do this. So actions now are captured as comments in the all file. So at least the engineer can say, oh, okay, so maybe I should add an action when the LLM is finished. No? So basically, starting from this competency question on top, which is what is the username of a player in a video game, you would say that the type is the player, the user has username is a data type property, then you have the labels and definitions, and the rationale would be, oh, this has been derived from CQ1 about the username of a player. I've added 3 examples that are not motivated by this CQ just to show an example of how it would look. So what are the stages that go through the agentic framework? Well, the first one is we have taken a little bit of a naive approach in the beginning. By naive, I mean basically we consider a little bit brute force in the beginning, but it kind of provided good initial results. So I hope that you bear with me. So the first stage is just the creation of a first ontology draft. As I said, we pass the structure in a JSON file of the previous table, and and the set of competency questions that we have to the LLM, and the LLM generates this JSON representation, which we convert into RDF. This can be done in different ways according to the state of the art. Question by question, by groups of common questions about a certain topic, because sometimes a term is derived from several competency questions, or giving all the XCQs. Now, one of the approaches that we were trying right now is just giving all the competency questions to the LLM, and surprisingly, well, LLMs of enough size produce good enough results. The next by the way, by doing this, sometimes the LLM will hallucinate some of the concepts. So we have a small fixing step that will fix URIs with the base URI of the ontology in case the LLM doesn't do it by default. Next, what we go through is a syntax repair stage by checking that the RDF that we have generated is correct. So we send the RDF to RDF leaf, and we go through an iteration of maximum 3 retries with an LLM to fix the issues. And it is true that during one of the problems of this approach is that by doing this loop, we may lose a little context if the LLM thinks that, oh, this triple is wrong. Okay, I will delete it, but I will not try to keep the original knowledge, right? So some knowledge may be lost. Then after that, we go into a logical consistency stage in which we check the RDF for consistent triples. And here, one of the observations that we have actually detected is that agents tend to be very lazy. So for example, if you have a conflict with a disjointness in between two of your concepts, it would say very well, I will remove the disjointness and proceed when maybe the error was in some other stage. So again, this is not perfect, but we wanted to have a baseline for comparing the quality of the produced ontologies. So far, the results, as I will show in a second, are quite okay. So basically, we go through a similar iteration, and we also check that there are no syntax errors as well. And finally, we go through the OOPS validator. In case you are not familiar with OOPS, it's a pitfall scanner for ontologies. And basically, it detects common patterns, anti-patterns in this case, for ontology development. No? So, for example, if you have missed a definition, it will tell you, hey, there's a definition that you're missing. If there are two properties that have a potential domain and range that could be inverse, it will tell you, hey, are you sure these properties that are not inverses could be inverses, and so on. So they have a catalog of, I think, more than 20 different types of pitfalls. And well, it also has a criticality associated with each pitfall. So what we do is that we take all the pitfalls that we can find, we send it to the agent, and based on that, the agent adds additional actions to the ontology. And then the iteration ends, and the engineer checks the quality of the ontology. So right now, we don't have a further loop going up to the competency questions, right? This is where we end, because we also believe that the human has to be involved in the creation of the ontology, since the ontology, it's a contract. Well, it's not a contract, it's like an agreement, right, between the different partners that are developed. So a step-by-step example in RDF would look as the following. No? So assuming that we have different competency questions, this is taken from an ontology about video games that is part of the Coral corpus, which is a corpus of ontologies with competency questions. And well, it will have things, let's assume that the model created this initial RDF snippet where it introduces a player and states that the player plays a game with the domain and range. It tells me the rationale and the source of each concept. And in this case, let's assume that the agent, because of something that it read in the competency questions or its own knowledge, stated that a player is a subclass of game and that is disjoint with game, which is a logical inconsistency, right? So next, the stage 2, the RBF is correct, so no repair is needed. And in the stage number 3, it will say something like, oh, okay, so there is an inconsistency. I will drop the disjointness action, but I will keep the subclass off, right? This is not the correct decision, right? Wanted to illustrate also with something that is not completely correct, but at least it removes the subclass action to restore satisfiability. Well, no, actually, it is the correct decision. No, it's removing the subclass action, and it states that it states that player is disjoint with game. And finally, after checking the pitfalls from the OOPS report, it starts at a missing inverse relationship between different object properties. And well, in this case, we are showing an inverse relationship that may have been missed between is played by and plays get, right? Which is correctly stated as well. And after this, well, the ontology thing, right? So now the question is how to evaluate this ontology that we have generated. This is also another challenge on which that's why I add a work in progress over here, because we have taken an initial approach, but by any means this is perfect. So one thing that you can do is, okay, well, comparing manually with the ground truth, but taking into account that there could be several ways of uh, modeling a concept, no? And the LLMs are usually try to use the language that appear in the competency questions, but the minute that the ground truth is reusing an existing ontology, the match is not going to be very easy to do, depending on which ontology has been reused. Usually manually also takes a little bit of time, and it may have some biases depending on the people who is the person who is evaluating this. So we looked into how to do it automatically, because you have benchmarks of ontologies and their competency questions. But the first thing that we realized is that, oh, surprise, the competency questions do not align very well with the final created ontologies. In, I think, all of the ontologies that we have been able to find with competency questions. So this is a problem. No? So also the generated terms and actions may be correct, but have a different representation. As I said, it is like the typical translation problem. Some competency questions may be in one language, but the terms may be in a different language, which is also a problem. And there is always the issue with contamination, which is, did the LLM already see this ontology before actually designing it? Then what's the point, no? Shouldn't you try with a different ontology? So what did we do to address this? In this initial evaluation, we tried to address these issues by doing different things. So first, we took competency questions of different size 5, 28, and 68. And two of the ontologies are designed from scratch by experts, because it's part of a project that we had. One ontology exists from the coral corpus, so contamination may have been an issue. And also we mixed languages. So in two of the ontologies, the competency questions are in Spanish, but the ontologies are in English, right? So there is this difference. While the last one, all the competency questions and the final ontology are in English. We try to do this to vary as much as we could, but of course, there are a few limitations. As for the generation and refinement, this is where some people may say, well, it's open source. It's open source for reproducibility, but the infrastructure is tricky, no? Because we use DeepSeek V3.2, which is a very big model. We are adapting this also to run with the Qwen 27B, so which is a little bit more reasonable for other infrastructure. And here are the versions of the tools and APIs that we use for different parts of the evaluation. So the metrics that we selected are, the first one is competency question coverage. That is how many of the competency questions are actually reflected in the final ontology. And then out of that, which is basically verified by hand, and then from the rest of the terms of the ontology, we do the matching between the labels. We tried doing exact match, sequence match, and semantic match using embeddings, because sometimes the embeddings provide quite very good results in the labels when they are not that well. And an important limitation of this evaluation is that we are not considering all action coverage. So we are working on this, but we are just checking a few things regarding the domains and ranges. But there are many points of improvement in this initial evaluation. These are some of the results, which, well, I promised numbers, so here are numbers. And the numbers in bold usually reflect that they are better. The question is, usually with these metrics, well, you can see some interesting stuff, no? Which is when the ontology is not very big, that is, it has like 5 competency questions, the coverage is high. At the moment you start adding more and more competency questions, we see that the model does not represent all the input knowledge that is over there, no? And that the more that we add, the more it tends to forget. Interestingly, we see that the exact match is rarely a very good metric because the models will use different synonyms or different wording, but that the semantic match is promising, but it has some limitations as well. So the good thing is that most of the concepts that are tracked by the input by the LLM are reflected one way or the other in the ontology. So let me show you an example because I work better with this. Taking the ontology that was a little bit the smaller one, you can see some interesting things. So one thing that you can see, the good things, is that the concepts are there, but sometimes are named differently. For example, you have on the left the ground truth, the gold standard, and on the right the one that was automatically generated. So what are the good things? That you have things like road segment, that was put, for some reason, the label must have been forgotten by the ontology engineers, but tramo in Spanish means road segment. So you have road segment and the relationship that road segment, well, the relationship with authorization is over there, right? It's validated on. And then you have permit, which is called authorization, which is in this case semantically equivalent. And things like the authorization and owner, they are reflected here with the corresponding where the corresponding object property linking everything together. So on the one hand is that this first draft of the ontology was actually quite, I was surprised by how good some of the results are because I was expecting it to be all over the place. Of course, this also depends on uh, the strength of the LLM that is underneath. Now let's see some of the errors that currently have. No, one that I see also very much in students is that they struggle quite a bit in distinguishing in main individuals, like when you have a list of individuals that you want to keep versus subclasses. No, this is a design decision, and it looks like the LLM decided, oh, I'm going to include all these types of regulated zones as subclasses, while in the source ontology, these were enumerated, it was an enumerated type of individuals. Then you see over here that unions of classes are missing, which is one of the limitations of the system, and that there are too many inverses. The thing about the inverses is curious, is because we are taking all the suggestions from OOPS at the same level, and one of the suggestions from OOPS is that there are potential inverses between every single pair of properties. So the model says, okay, I'm gonna just do the easiest thing, which is add a lot of inverses, even when maybe it doesn't make sense to add them. No? So I hope that with this I've shown you like what are the good and what are the bad things that we can obtain. So what are the lessons learned that we obtain from this effort is that we still believe that LLMs should be involved, that they're very valuable asset when you have the provenance of each term included. They give you a very nice starting point for generating the ontologies. But if we really want to progress in this task, we need to make sure that CQs are correctly aligned with the final ontologies, which is interesting because to me, like CQs have always been the contract the requirements that we have to follow as ontology engineers, but we have found very big divergences between the CQs and the final ontology. So, well, I've mentioned already some of the limitations of the framework, like we don't recheck, for example, CQ coverage in each step. There are many tools missing. For example, we don't have any agentic approach for reuse. We haven't addressed the problem of concept reconciliation with the smaller LLMs, and that we are moving towards also adopting smaller LLMs because DeepSeek, not everyone can apply it in their own infrastructure, right? So with this, I wanted to more or less in the talk, I think I have convinced you or produced some excitement in how LLMs can be used to create or assist in ontology creation, and how this framework provides a promising baseline to compare against. We actually created it in the scope of another project, which is to evaluate this type of activities. But what we need a little bit of improvement. Well, there are many points of improvement. So if this can inspire you to create different architectures and play around, we'll be happy to test. And the GitHub repository is done. So feel free to open issues and let us know if something's not working. These are some of the references that I use. I wanted to also acknowledge my colleagues, Maria Poveda, Jiayi Li, and Clark Wong. And this is done in the context of SOEL, which is another project that we have for checking how basically it's addressing more into the evaluation part, which is also part of the work that we are aiming towards. No? So if you have any questions, please let me know. And with this, I finish the presentation. Thank you very much.